So this video is going to be about Heisenberg. It was Heisenberg Uncertainty Principle. Uncertainty Principle. Principle that if we have a particle, let's say an electron, we all know that it will behave as particle and wave depending on the observation, meaning that means that if, let's suppose there's a person over here, or there's observer over here, and he is observing at this particle. So this particle electron, then it will move straight, and it will move straight. It will be a particle. It will act as a particle. But if there is no observation, what will happen is that this particle electron, it will travel as wave, and each point in this wave, it's to be more specific, this is how it should look like for a particle, and this area defines where that particle can be in this area. The and this you can calculate using this symbol psi, and mostly we take its square, which we take its square, and the square tells us the probability, because quantum mechanics is all about probability. We don't and it's not correct, it's not always or it's not correct, as whenever, let's suppose, whatever value we get over here, and if that value, let's suppose that value says the particle will be found here, higher chances, we say high probability. But to our expectation, that doesn't happen. The electron is found here, where it is. Okay, so coming back to Heisenberg uncertainty principle, he said that if an object, or if a particle is moving through space, it will act as wave, and it will act as particle. That, let's suppose someone is not observing it, it's a wave. Let's suppose suddenly an observer comes. What will happen? It will turn into a dot particle. So Heisenberg uncertainty principle says if it's moving, as it's moving, it has what? It has momentum. It has momentum. And when it's not moving, what does it have? It has position. So Heisenberg uncertainty principle says that you or we cannot cannot and when I say cannot, it means it is cannot measure both quantities. In quantum mechanics, they both act as operator. As far as I know, momentum is a operator in quantum mechanics, and it's mostly like this. So cannot measure both properties at the same time. Now it's not finished yet, because most people take it to as, it's saying that if someone wants to know the property, let's suppose someone wants to know its momentum, he will just know this momentum, and he will not, and that point, sorry, momentum only, and at that point now he doesn't know what is its position. So that's wrong. He does know its position, but when I finish my sentence, what I'm trying to say is that at the same time, measure both at the same quantities at the same time without, cannot measure both quantities at the same time without increasing, or wait, without decreasing precision. So precise measurement of other quantity. So that means you can measure both at the same time. It's not like you cannot measure both at the same time. You can know one at the same time. That's wrong. You can know both at the same time, but it will decrease the precision level, the value. Let's suppose there's a certain value for momentum that we got, and there's a certain value for, it should be like this. It should be like this. And there's a certain value we got for position. So if you measure momentum, it will decrease, it will decrease the value, it will decrease the precision level, the accuracy level for the position, that we will not know where. Now it will be harder to know where it is, but we still know it is, we can know where it is, but it's now the level of precision or that accuracy went down, and for the momentum it went up. So we can say that they both cannot be known at the same time, and they both equal a certain constant. So then there's an equation, Heisenberg uncertainty equation, Heisenberg uncertainty uncertainty equation. So the number one equation, as we both know, these two are the quantities of that equation. So now we have something new here. This is what we call H bar. This is a bar, so it's called H bar Planck, and it's also known as, okay, wait, I'll write here. It is known as reduced Planck's constant. We have discussed about what is Planck's constant. Mostly Planck's constant is used for describing the quantum nature of particle, because when we write the value for H, it's 6.63 times 10 to the power minus 34 J dot S. Joules, this is joules. Or wait, let me write joules dot second. So look, minus 34, that's way too low. So this is used for keeping the quantum level, the scale level at a low level, measurements. So then again, momentum and position both can be known at the same time, but it decreases the precision level of knowing one will affect other quantities or other operators precision level. So then there's one more as well. There's one for momentum and position, which is, and if we want to illustrate it way in a diagram, if this is a wave with momentum, then this is a particle which has position. But it does make sense, because when you're looking at it, it will act as a particle, and when it will act as a particle, and you will see it in one spot. And when you, because when it's in a wave function, actually it's in a superposition state. It stays superposition state, and as we know, superposition state mean it's in all these. It's here, it's here, it's here, it's here, it's here, it's here, it's here. Whatever possible location you can know, it's there. But when we try to measure it, then we can come to know that where it actually is. And how we measure it, we have discussed. It's using this symbol, and this symbol is known as wave function. Wave function. And if we want to know the meaning, the meaning is, if I write it, the probability of finding the particle in a certain space. What I mean by space is area, a certain area. So because at quantum level, everything goes beyond what we imagine, and everything is in probabilities. Always remember, in quantum level, probability is the key. As we cannot get certain, or we cannot get that accurate answers. So then there's one more, like this is momentum and position one, and then we have energy and time. The most famous one is momentum and position, but energy and time is also the same. As we look mostly, we capture, or the main ones are momentum and position, but it's the same. The more you know about energy of the particle, the less you know where it is in time. And this is actually this wave function over here. This tells us about the evolution of particle through time. There's one which is about only x. Here it's only position, but here it's about position and time. So here again it's the same thing. We are just recapping. If you know energy, the precision level of time will decrease. If you know time, it's evolution through time. Its energy, how much energy it has, will decrease. And this is just to stable, because h bar is a very small value, and divided by 2 makes it even smaller. So this is to keep the scale level how do you say, scale level control. And so then what else we can say? We have so yeah, that's it.